In this video, we're going to discuss the solutions to the second homework. So most of these were just about translating the sentences into variables and then realizing some sort of equivalency, some sort of distribution law, some sort of algebraic law that we discussed. Okay, so the first question, if a man works hard, then the land will not be lazy. Okay, so this is of the form P, if P, then Q, and the contrapositive, right? So if you have P implies Q, the contrapositive of that is not Q implies not P. So basically we want to take the second half of this sentence, negate it, and then imply the first half and negate it. So if we take the second half, it says the land will not be lazy. So we should put that at the beginning and say if it's not the case, the land will not be lazy, right? What is that? Well, that's just if the land will be lazy. If you negate the not, you just get rid of it. And then you take the first half and put it at the end and negate it. If a man works hard, that would become then a man does not work hard. So basically, the first question is recognizing that a statement is equivalent to its contrapositive. Question 2, I discussed this in one of the videos, but basically when you have the triple equal sign, this means that the two statements on the left and the right of the triple equal sign are equivalent, logically equivalent, and for the purposes of this course, they are deemed logically equivalent if they give the same output in a truth table. So the answer is D. But I'm actually going to go ahead and show that really quick. So we wanted to show that P is equivalent to, let's see, yeah, P, Q, R. Okay, so it's P, Q, R, and I want to show that's equivalent to P, Q, R. Okay, so I'm going to do this table first. So if I have P, Q, and R, and then I have P or Q, and then P, Q, or R, how many rows do I need? Well, I need 8 rows, right? Because there's 3 variables. Okay, so 8 rows. Let's see, 1, 2, 3, 4. Okay, so that should be 8. First, we're going to assume that everything is true. Then we go through and make the last one false. So true, false, true, true, false, 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 true, true, false, true, false, 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 true, and false, false, false. Okay, and then in a different color, I'm going to go ahead and do QR, and P or Q or R. Okay, and so basically what we want to show is that for whatever values of P, Q, and R that we give, that these two columns here, they're going to give the same output. And it is pretty obvious once you see it. Okay, so P or Q is true as long as one of them is true. So let's look down here really quick. True, 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 true. Okay, so everything is going to be true in this column except for right here in the next to last column. So these are all true. And from this value here, that's going to make this true, right? Provided a value in here is true. Or R, as long as one of them is true. So all of these, because all of these are true, right, except for the last one, the last two, those are both false. These are definitely going to be true, right? And now we should ask, okay, is this value here going to be true or false? Well, that entirely depends on R, right? Because P or Q is definitely false. So what is R? Well, here it's true, so that's going to be true. And if R is false, the whole thing is false. So the moral of the story, right, is that they all have to be false for this to be false, right? And I think it's pretty obvious to see now that they're equivalent, but let's go ahead and finish it. So Q and R, I'm going to go ahead and use a different color. Let's use black. So anytime I see a true Q, so that's true, true. Okay, here Q is false, but R is true. Q or R right here, they're both false, so this is going to be false. We have true here, and true, and true, and false. So now I'm going to go ahead and anytime I see a true in the previous column, I'm going to go ahead and write it over here. So I only have these two spots left to check. And because the truth can only change from P, I should check P. Okay, so here P is true, so I'm going to go ahead and put true here. And in the final row, I check P and it's false. So if we just compare the final columns, right, this column and this column, right, we see that every time you have a true here, for every value you have in each row, the rows match, right? True and true, true and true, and so on, all the way to the end until you get to false. So that proves, in fact, that this triple equal sign is warranted. In other words, they're logically equivalent. But the answer was just construct a truth table, compare these tables. If the final columns are identical, they're equivalent. And that's exactly what we did. We did it as a single table, but you could just as well do it as two tables. And that's what I mean by final column, right? Okay, so why are these equivalent? Okay, so this is the distribution law. I did discuss this in the algebra of propositions video, but I'm going to go over it really quick in case it's not clear. So you have not P Let's use different letters. So how about, let's see, R or P and Q. And this is going to be logically equivalent to R or P and R or Q. This is just the distribution law. Okay, if this is not clear, go ahead and rewatch the algebra of propositions video. But one way to think of this is that the V symbol, that kind of acts like addition, and the uh, wedge symbol, that kind of acts like multiplication. And so it's it's distributing, right? That's basically what's happening. Okay, so in the particular example, you just let R equal, okay, set it equal to not P. And here I don't mean equal, logically equal, I just mean set it equal to, right? So I'm saying let's call R, let's let R equal not P, and then every time you see R, plug in not P, and that's exactly what you have in the question. Okay, so number 4, this is pretty straightforward. So if 3 is less than 2, then -3 is less than 7. Okay, so this is very true, right? Very much true. So if the first half of an if-then statement is false, the whole thing is true, right? So 3 is not less than 2, so the whole thing is true. Remember, the only time a if-then statement is false is if the first half is true and the second half is false. Okay, so here we have another truth table. Um, let's go ahead and go through that real quick. We have um, let's see, we have PQ and not P or Q implies P. Okay, so P, Q, and not P or Q implies P. Okay, so we have two variables, so we're going to need 2 to the 2 rows, 4 rows. So that shouldn't be so time consuming, pretty straightforward. And let me pick a different color. Okay, so I'm going to write that, and then I'm going to write this, and then for the final part, we have that right there. Okay, so let's split this up, and there should be 4 rows, right? Okay, not the best table, but it'll work. Okay, so P could be true, and Q could be true. I need a column here, okay. And Q could be true, P could be true, and Q could be false. P could be false, and Q could be true, and they could both be false. Okay, so far this is just the setup, right? That's exactly what we have, right? Okay, so what we wanted to know was these final spots. I called them 1, 2, 3, and 4. And in the intermediate, you should have added these other steps, right? Just on your own uh, sheet of paper, and then deduce the final part, right? So if you have P is true, then not P is false. And if P is false, then not P is true. And this statement here is going to be true as long as at least one value is true. Otherwise, if both are false, the whole thing is false. So because not p here is true, this is going to be true. And because q is true, this is going to be true. And effectively, the one thing that makes it false, right, is when q is false and not p is false. So that's right here. Okay, also you might, if you're closely paying attention, you might recognize that not p or q, this is just another name for p implies q. Okay, p implies q. Okay, so what about this implication symbol? Okay, so this is going to be true as long as this is false, right? So that's one way. So because the antecedent is false, the whole thing is true. And otherwise, if the antecedent, the first part, as long as that is true, then we have to look at p, and if p is true, the whole thing is true. Otherwise, if the antecedent is true and the consequent p is false, the whole thing is false, right? So the rest of the cases are true, so all we have left to do is look at q. Okay, so the first and third row, q is true, so those are going to be true, right? Because the first part is true and the second part is true, right? But in the final row, you have the first part being true and the last part being false, so the whole thing is false, right? So the answer should be true, 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 false. Okay, and ooh, okay, hold on. Okay, so it looks like I have a typo in the solution key. I'll have to fix that. Sorry about that. Please email me if you have a concern. Actually, oh, no, okay, sorry. No, it looks like I read this. Oh, I was looking at the Q column when I was doing this, not the P column. So I don't have a typo in the key. I misread this. So let's go ahead and uh, let's just redo that because I feel like I may have confused y'all. Let's just redo the last column. Okay, so if the first half is false, the whole thing is true, right? So that's true. And then if this is true, we then want to look at P. So true, true, and true. So let's look at P. That's here. Okay, so this is true. So because both of them are true, this is true. And okay, this is true. So is P true? No, it's false. So the whole thing is false. And for the final part, again, P is false. So this whole thing is false. Okay, so yeah, so apologies. When I was evaluating the final column, I was looking at the second column, Q, instead of P. So yeah, it's really important to double check your work. And that's actually the solution. Okay, if an argument does not use valid reasoning, it is called a fallacy, right? So no other answer is, I mean, this was a giveaway, right? Okay, 7. Okay, so part B is valid, and why is that? Okay, so not P implies not Q is equivalent to Q implies P, right? Q, this is Q implies P. And because Q implies P, and you have Q, then you can get P. Okay, so let me go ahead and do that again. So you have not Q implies, sorry, not P implies not Q, comma just means and, Q, and then this little turnstile, P, and remember, as long as everything to the left of the symbol, if you have those assumptions, the question is, well, can you get the thing on the right? And when you're building an argument, you can take any of the premises and transform them into logically equivalent things. So this is just Q implies P, and then you have Q, and by modus ponens, you arrive at Q. There is also a name just for this inference. I don't quite remember if I taught you that. The book goes into it, but this approach I gave here is also good. Okay, so the second example, or the first example rather, is not P implies Q and P, therefore not Q. Okay, so this is invalid, and if you think about some examples, um, I'm sure we can refute it. Okay, so how about let's see. How about P is does not. Okay, how about Tim does not exercise? Tim does not exercise. And then Q will be Tim becomes very strong. Okay, so not P would be Tim Tim does exercise, sorry. Tim does exercise. So not P implies Q is Tim does exercise, therefore Tim becomes very strong. So, sorry, it's if Tim exercises, if Tim does exercise, Tim becomes very strong. So if Tim does exercise, then Tim becomes very strong. Okay, so we're assuming, so anything on the left-hand side, you're allowed to assume. Okay, and these seem like pretty reasonable assumptions. You know, if you exercise, you'll become strong. And then basically what this argument is saying is that, in fact, Tim does not exercise, right? But then what they're inferring, right, with not Q is that Tim does not become very strong, right? But we all know those people that don't exercise but are very strong, right? So even if the assumption here, you know, I mean, it's not a perfect assumption, but it's pretty good. You can, if you don't like exercise and strong, you can think study and get good grades. Um, or I mean, if you want to go even more uh, with less assumptions, I guess we could use mathematical statements, right? So use 2 plus 2 or whatever. But the point here is that it's making a bad inference, okay? Or the other thing you can do is, because you had to match, right? You just recognize that one is valid and the other has to be invalid. Okay, so question 8. If Jack works and does not play, then Jack is a dull boy. And the hint was to convert that statement into a logical statement using P, Q, and R. So Jack works would be P. So, oops. So P, and let's do this like this. There we go. Okay, so this of course comes, well, it's in the Shining, the reference, but it's actually before the Shining. Okay, so if Jack works and does not play, so P and Q, right? If P and Q, then Jack is a dull boy, right? Then R, right? Okay, or I could also write P and Q R. These are the same thing, okay? Okay, so anytime I have a implies sort of thing, I can rewrite that as not, and then whatever is on the left-hand side, and then or, and then whatever is on the right-hand side, okay? Now, I have this not followed by P and Q, and by the De Morgan law, I can distribute that through the parentheses and flip the pointy arrow thing, right? The and. So this will become not P or not Q or R, right? So the not only distributes where there's parentheses. So here we have a long set of ors, right? So if we translate this back into plain English, this says um, not P or not Q or R. So um, Jack does not work, or Jack does not play, or Jack is a dull boy, right? So that's also equivalent to saying Jack does not work, Jack does play, or Jack is a dull boy. But that's also equivalent to either Jack does not work, or he does play, or he is a dull boy. So the answer is A. Okay, this right here, just finding the contrapositive, right? You just take the second half, negate it, and then take the first half and negate it. So um, take the second half, put it at the beginning, right? That's what we did here, and then negate it. And negating it in this case means equals becomes not equals, right? So it's not the case that x squared equals 9, which is equivalent to saying x squared is not equal to 9. So if it's not the case that x squared equals 9, then it's not the case that x equals 3. That's what we're looking for. And that's the first choice. Okay, and this last one, pretty straightforward. Let's do that in blue. So you have not P implies Q, and before I reveal the other half, let's just do what we did here, right? So, sorry, what we did a few problems ago. So first off, just recognize that P implies Q. This is equivalent to not P or Q. And again, I can distribute this through. So that's going to be not P and not Q. And I can get rid of the, I can rewrite that as not P and not Q. I just added parentheses. Okay, and that's exactly the answer. And for that matter, it would also be equivalent to P and not Q, or not Q and P, right? There's a lot of things it's equivalent to, but the question just asked us to show that equivalence. So, okay, that's everything. If you have any other questions, please feel free to email me. Have a good day.